Hey, welcome back. This is 14.2, and we're going to try to connect the iterated integral to volume. Okay, so in the beginning, we just sort of start with kind of building the Riemann sum like we did in Calc 1. Um, so if you want, I can kind of remind you of what we did in Calc 1. For some reason, my pen isn't working. I'm trying to get it to work. Maybe it's because my shirt is on it. Okay, there we go. So, first, again, we kind of build our Riemann sum to approximate the area under, or in this case, the volume underneath the surface. So before, the way that worked is you had some sort of curve in 2 dimensions. You're integrating from A to B, and then you just chop it up into a bunch of little rectangles. Usually we had equal widths. I know it doesn't look like I have an equal width there, and we call those change in x's. And then we can just figure out the area of like one particular rectangle, call it a change in a sub I, which is usually f of x sub I times change in x. And then to get the approximation of the area underneath the curve, we sum up all of those rectangles, and then we would take the limit as the width of those intervals goes to 0. So I guess the change in x goes to 0, and then that would give us our integral from a to b of f of x dx. Okay, we want to kind of pull the same business here, except we're not going to sort of end with the iterated integral. We'll have this thing that represents the volume underneath the surface. So now we're in 3 dimensions. Instead of just a plain curve, we have a surface. And instead of having like an interval that we're integrating over, we'll actually have an area that we integrate over. Okay, so let me draw some sort of surface over this little kind of circular quarter of a circle type region. Okay, so it's kind of like this. Okay, so basically I'm trying to figure out the area underneath the surface above the xy plane. So instead of chopping up an interval into a bunch of change in x's, I'm going to chop up the area underneath the surface into a bunch of little change in rectangles or change in areas. Okay, so I'm going to chop it up into a bunch of rectangles. Okay, and I'll have a bunch of these things, these change in a sub i's, I guess I could call them, which is basically like a change in x times change in y. It's basically length times width. Okay. In order to produce this limit at the end, like we did in Calc 1, I'm going to use, instead of change in x, I'm going to use this thing called a norm. And the norm is going to be the length of the largest diagonal. So in this little picture, it looks like maybe this would be the longest diagonal. And what we'll end up doing is letting that diagonal go to 0 in order to get better and better approximations and ultimately find the actual volume, right? So in this case, this object here, this delta with the absolute values on steroids around it, we're calling that thing the norm, and that represents that longest diagonal amongst all of the rectangles. Okay, so we're going to pick points in these rectangles. Back when you did in Calc 1, you picked left-hand endpoints, right-hand endpoints, or midpoints. And the exercises in the homework and in the examples in the book, they're usually picking the middle as your point. So you can imagine picking this point as kind of the point that you'll use in order to determine the height of this rectangular solid that's going to, we can actually take a look at what it looks like. So let me redraw my surface. Okay. You become kind of good at art if you take Calc 3. So here's my surface, and I'm going to produce, instead of a bunch of rectangles, I'm producing a bunch of, what do they call them? Rectangular solids. Okay, so using, I should use the midpoint, goes up and then to to the surface. I'm trying to figure out the area, the volume of that blue thing there. Okay. So I guess I could call that change in v sub I, and to get that volume, instead of so up here it corresponds to this object, right? So in order to get the volume now, I basically have to take the height of that thing, which will be given by f of whatever that point is I chose, f of x sub I comma y sub I, and then its height is going, or sorry, that is the height, and then times the area of the base, which is going to be that change in a sub I. Okay. Then to get an approximation for the volume, you just add up all those delta v sub i's, and if you take the limit as the norm goes to 0, you end up with what we're going to call the double integral over r of f. Okay, so we symbolize it using this double integral looking thing. Okay. All right. We've not really connected this to the iterated integral. I mean, it looks like an iterated integral and all that jazz, but technically we haven't really made that connection. Okay, you need to have a theorem that will say that this works. So before we get there, though, we're just going to kind of do an example where we get an approximation for the volume underneath the surface, and we could look at problem 1 and the exercises. So problem 1, we want to approximate the integral, which is the double integral of f over the region R, where the region R is given by these 4 vertices. So we can draw the region R here, 0, 0, and 2, 0, and then 1, 2, 4, 0, and then we have 2, 4 on there. So we're integrating over this region. The book wants us to divide this rectangular region into 8 parts, so it's pretty easy. Just chop it up into 8 parts. And then for the surface over top of this region, it's given by the function f of xy, excuse me, equals x plus y. Okay, so we're going to use midpoints in order to determine that height above those rectangles. So we're using these points here, and I need coordinates for all those points. Okay, so the coordinates, because they're midpoints, it's just going to be for this first guy right here that I just put in black. That'll be at 1/2 comma 1/2, and then I'm going to go across like this, right? So I just move the y coordinate over by 1. So the second one would be 1/2 comma 3/2, and then I have 1/2 comma 5/2, and then 1/2 comma 7/2, and then for the next set of 4, you add 1 to the x coordinate. So instead of 1/2 all the time, you'll have now 3/2, and then the y coordinate will be the same. So 3/2, 1/2, 3/2. I mean, the same as before. It won't always be 1/2. It's changing just like it does before. Okay. So that would be the second one, and then 3/2, 5/2, and then 3/2, 7/2. Okay. Okay. So the area of one particular one of these, because of course for the volume increment, we're going to need f of x sub I comma y sub I times change in a sub I, right? So let's figure out what the area increment is, and it's always the same because of the way we've developed our squares here. The area will just be length times width, and of course this length here is just 1, and then the width on the y-axis is also just 1. So it looks like the area dimension is just going to be 1 times 1, in other words 1. So to figure out the volume for any particular rectangle, all I have to do is really just figure out f of x sub I comma y sub I. And for us in this particular example, that will just be add the x and y coordinates together. Okay. So for our approximation, we're going to sum all of those up, and it'll just turn into the sum of the components. right? So for the first one, you go 1/2 plus 1/2, which is 1. Okay, so I basically just did this one. And then the next one, 1/2 plus 3/2 is 4/2, which is 2, and then so on, right? So the third one is 6/2 is 3, 8/2 is 4. Down to the second row now, 4/2 is 2, 6/2 is 3, 8/2 is 4, 10/2 is 5. So an approximation of the volume underneath that surface is going to be 24, I think, right? So 5, 10, 24, yeah. Okay, we want to connect that to the iterated integral. That's kind of what they're doing here, and the way it'll work is basically you just integrate like we did in the previous section in 14.1. You want to set up an integral for this region, and in the integrand you're just going to put the surface that you're integrating under. Okay, so you're going to have a double integral of the f of x function. I'm going to go the regular orientation dy dx. So y equals 0 to y equals 4. And then x equals 0 here to x equals 2. Okay. 0 to 2, and then integrate that guy, and you get hopefully something similar to what we just figured, right? If these are the same things. So the first, with respect to y, that would be xy, and then plus y squared over 2. Evaluate, and then dx. So 0 to 4. So I'm getting place 4 in for y, so 4x plus 16 over 2 is 8 dx. And so we get 4x squared over 2 is 2x squared plus 8x from 0 to 2 now. So 8 plus 16, and yeah, 24, right on the nose. So at least in this case, it seems the iterated integral and the double integral, or the approximation of the double integral anyways, are kind of the same thing. And that's what they start exploring in the next part of the book, where they are evaluating these double integrals. So section 2, evaluating double integrals. Okay, so they're trying to sell you on this idea that the double integral is basically just an iterated integral. And I'll do kind of, I guess we could, do I want to work with this example? I'm going to make up my own example. Okay, my example is a little easier. All right, so my surface is z equals y over 2, and the region I'm integrating over is this rectangular region given by these inequalities. Okay, all right, so the curve y over 2, and note I'm going from y equals 0 to 2, so I'm just going to draw that over that interval. Okay, so y over 2, that if this is the yz plane, I have a line going through the origin with slope 1/2. So I go up 1 and over 2, and that's what my curve, well, at least the trace of this plane, that's what it looks like in the yz plane. Okay. Then if I want to extend that in the x direction, from 0 to 4, okay, so I'll go from 0 to about right here, 4. It's basically, it's going to be like taking this triangle and just stretching it in the x direction. So you can imagine kind of this scenario going on. Just kind of butchered it. Oh well, I think you get the idea. That's what it'll look like in the XYZ plane. Okay. So what we're after is trying to evaluate the volume of this kind of triangular thing that we've generated. Right. All right. What the book is going to try to sell you on is that you can evaluate it by first figuring out the area of this triangle and then adding up the area of that triangle as you vary on the x-axis from 0 to 4. Okay, so first you have to get the area of that red triangle. So again, in the YZ plane, we can produce an integral that will give us a formula for that area, right? So y z, and again, we're going from 0 to 2, and here is our curve. We want basically that area. So how do I get that area? It's just an integral, right? So it's the integral from 0 to 2 of y over 2 with respect to y. Okay. And again, that thing I just figured out is going to be the area of that red triangle. So to get the volume, what the book claims is then you could take the integral of that thing from 0 to 4 on the x-axis, and that will tell you the volume of the entire guy. And what you're looking at then is basically just your iterated integral. Okay, so this innermost integral then, again, it should just be the area of that triangle. You can figure out the area of geometrically. It's just 1/2 base, which is 2, times height from the slope is 1. So it should be 1, right? That inner integral should be 1. So let's evaluate it. I get the integral y squared over 4 from 0 to 2 dx. So it's going to be 4 over 4, which, yeah, it's 1 dx. And then we integrate from 0 to 4. So that's just going to be x from 0 to 4, and then plugging in the limit into the antiderivative, it's 4. So supposedly that's the volume of that region. In the book, the example they do, the little triangle is variable. So when you find the area of that triangle, it should be some variable expression in terms of x. And then as you integrate on the x-axis, you're integrating variable-sized triangles. But the idea is the same. Adding up all these little triangles, if you add them all together from x equals 0 to 2 on this picture on the right here I'm looking at, in figure 14.14, if you're going from 0 to 2, adding up all these little triangles of varying sizes, you end up with the volume of that triangular solid. Okay. So then they kind of claim, and without too much proof beyond what they just showed you, that the double integral is the same as the iterated integral. Okay, so that this thing again, this what this thing is called is the double integral of f over the region R. Okay, and now what you're seeing in this theorem 14.2 is that those guys, the iterated integral and the double integral, are the same. Okay, so theorem 14.2, the double integral of f over R is equal to the iterated integral from 14.1. Iterated integral. Okay, from there they're just going to look at a bunch of kind of random problems in the exercises. Okay, and it works basically the way the iterated integrals work. You basically set up the limits on your integrals based off of whatever region you're integrating over, and then the surface you just kind of spackle that in to the integrand. Okay, so the surface for number 3 would be x plus y in space. Okay, so we just kind of want to go through and look at these examples. And yeah, so let's just look at some random examples from the homework. Random examples. Okay, so one note, the example they have in the book, oh my gosh, are you kidding me? This one here, example 3, that integral is ridiculous. I don't know what they were thinking putting it in there. Maybe they're trying to impress everybody. I don't know. So the integral here, there's all kinds of like crazy kind of algebra that you need to get from the second step to the third step. Then once you get there, you need to do a trig sub. Then you basically need to do reduction formulas. Then you need backs. It is just literally a 2-page integral, you know. They use Wallace's formula, which makes it at least a little bit quicker, but most people don't have Wallace's formula memorized. So, do example 3 on your own risk, at your own risk. I'm not going to do it. I'm just going to skip it and go to the homework exercises. Okay, so hopefully that doesn't upset you, but there it is. Okay, so let's look at number 3. Sketch the region and then evaluate. So 0 to the 30, y over 2 to 15. They always give you crazy limits because it's computer generated. Right, so to sketch this thing, it's basically just a 14.1 problem, right? I want to go from x equals y over 2 to x equals 15. The dx dy is a non-standard orientation, so basically you're running up the flagpole, right? So you're going in this direction. X equals y over 2. You may have an easier time of graphing the other version, so if you solve for y and just graph that might be easier for you. Y equals 2x. So the slope go up 2 and then over 1. So it's kind of looking like this. The only unfortunate part is I think we have to go all the way up to x equals 15, right? So anyways, that's the curve x equals y over 2. And then we need to go x equals 15, which is way out there somewhere. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, I guess. It's this curve. Okay, and we'll kind of, this intersection point, we'll probably need that point. So what is it? It's x is 15, so y is 2 times 15 is 30. All right, so that's 1530. Okay, so I'm going curve to curve, and then point to point. So on the y-axis, I'm going from 0 to 30. So the region I'm integrating over is this region right here. So that would be 15 to 30. So I already clicked that in there. That's the first region given. Then they actually want you to integrate the thing. Unfortunately, the limits are nasty. Let's take a look anyways. With respect to x, it would be x squared over 2 plus xy. And then what do we have? From y over 2 to 15, apparently. dy. So this will be equal to the integral 15 squared, I think it's 225 all over 2 plus 15y, and then minus, so that'd be like y squared over 4 times 2, so y squared over 8 plus y squared over 2 dy. I think it's 225. Yeah, 225. I did it earlier. So this, let's combine some like terms, I guess. So not much really to do. 225 over 2 plus 15y. And then you can find a common denominator here. So this would be apparently 5y squared, so minus 5y squared over 8 dy. And then we're integrating from something 0 to 30. It's awfully nice of them. So 225 all over 2y plus 15y squared over 2 minus 5y cubed over 24 from 0 to 30. So I'm going to cheat a little with Wolfram here. 225 times 30 divided by 2 plus 15 times 30 squared divided by 2 minus 5 times 30 cubed divided by 24. It's 4,500, really? That's kind of odd. All right, so minus 0, yeah, 4,500. Let's make sure it's right. Whoops, and I just put in 45,000. Oh, it didn't take it. Thank you. Drum roll. 3 years later, and it's right. Okay, great. So here we have more of an oddly shaped region. Let's skip that one. Well, here's one of the annoying ones where you have two regions that you're integrating over. You need two integrals to do it. So number 5, then sketch the region R that you're integrating over. So y minus 5 to 0, e to the x plus y, dx dy plus from 0 to 5, and then 0 to 5 minus y, e to the x plus y, dx dy. Let's make this the video quiz. Okay, so this is the second video quiz, and video quiz set number 7, and it's problem 5 in WebAssign. Okay, great. Hopefully we can do it, right? Okay, so the first integral is going from x equals y minus 5 to x equals 0. Again, it might be easier to rewrite that to graph it. So this is actually y equals x plus 5. On the y-axis, I'm going from 0 to 5, so it's that weird orientation. Right, so the curve y equals x plus 5 has an intercept at 1, 2, 3, 4, 5 here. And so I'm going from x equals 0, which is the x-axis. Oh, sorry, no, that's the y-axis. Whoops, that's the top. X equals y minus 5 to x equals 0. That's kind of weird, right? That's like in the other direction. X equals 0 anyways is the y-axis, so that's like the top curve, and the y minus 5 is the lower curve. Let's get the intercept of x plus y equals x plus 5. So the x-intercept is, the y-intercept's at 5, the x-intercept though, let y equals 0. So x will be negative 5. So 1, 2, 3, 4, 5. So our bottom curve is right here. Okay. So curve the curve, bottom curve to top curve, and then point to point on the y-axis is going from there to there. So that'd be the first region from the first integral. The second integral then, and again you may want to rewrite it, the top line. So the top curve is x equals 5 minus y. So rewriting it, y equals 5 minus x then. So it has a negative slope. The y-intercept is at 5. The x-intercept is 5. So 1, 2, 3, 4, 5 right here. And the curve, or the line in this case, is this guy. So I'm going from x equals 0, this time is right here, to x equals 5 minus y, which is that curve. On the y-axis, I'm going from 0 to 5. Okay, so that will be this region for that second curve. So it looks like the first is the appropriate region. I'm going to rewrite the heck out of that integral, right? I don't know, there's no way I'm doing two integrals today. Two separate integrals to figure out one problem. So what you do instead is I mean, really, I don't even see why it would be necessary to have written it in this way, because the truth is you could just, let me do this in green, you could start here and then just integrate to this top curve here, right, and then go from there to there. I don't see why that's I don't see why they needed to complexify the issue. So let's just do that, right? It'll be 0 to 5 of the integral. I have a sneeze coming on. Sorry. Yeah, so 0 to 5, and the bottom line, this bottom one here, is the y minus 5, and then we'll go to the top one, which is 5 minus y, right? And then e to the x plus y. Maybe you can't even integrate it. I don't know. Dx dy. Okay, so hopefully we can integrate it. If you can't integrate it, you literally have to change the order and then rewrite the integral again, which would be a bummer. Okay, so anyways, integrating with respect to x, e to the x plus y, what is that? E to the x plus y is the same as e to the x times e to the y. So integrating that thing, you just pretend that the e to the y part is constant, right? And then the integral of e to the x is just e to the x. So you get e to the x times e to the y, and of course then we're subbing in for x, y minus 5, and then 5 minus y dy. And so let's see what that is. E to the 5 minus y times e to the y minus e to the y minus 5 times e to the y dy. You have like bases, so you're adding exponents. 5 minus y plus 5 is e to the 5, or sorry, 5 minus y plus y is e to the 5. Then minus e to the y minus 5 plus y is 2y minus 5. Okay, and then dy. Then I have to integrate that thing. If you want to, you could do, well, the first guy is just, a constant, e to the 5y. The second guy, you may have to do a u sub on. If you do a u sub, you're going to get a constant 1/2 floating out, right? 1/2 dy. So when all is said and done, there'll be a constant of 2 floating out. So when you take the reciprocal, you get a 2, so you can spackle a 2 onto here, and then you have e to the 2y minus 5 if you wish. And then finally, I think we can integrate 0 to the 5. So I'll have 5e to the 5 minus 2e to the 10 minus 5, which is 5, minus 0 minus 2e to the, I guess, just negative 5. You plug in 0. So this will be 3e to the 5 plus 2e to the negative 5. Believe it or not. Okay, so let's see if that's right. 3e to the 5 plus 2e to the negative 5. And then drum roll, please. Please be right. Please be right. Please be right. Oh! Oh, I see it. This is what happens when I try to do too much in my head. This is just 2, and then the constant is 1/2. I think it was kind of even saying that, So the constant is 1/2, not 2. So this will be 1/2. This will be 1/2. To combine these two, I need a common denominator. So 10 halves e to the 5 minus 1/2 e to the 5 is 9 halves e to the 5, then plus 1/2 e to the negative 5. So try 2. 9 halves e to the 5 plus 1/2 e to the negative 5. So mission. Like, I know that's right. Okay, whatever. Right. So all right, so 6 and 7, now they're going to start forcing you to kind of set up 2 different orders of operations. Usually when you're dealing with a rectangular area, that's pretty simple. There's not really anything all that crazy that you have to do. When your limits become lines, though, then yeah, it becomes a little bit harder. Okay, so we want to investigate maybe one of the harder ones and see what's going on there. So number 8. Okay, so I want to set up both orders of integration and then integrate the easier one. And what we're dealing with for our region is y equals x, y equals 6x, x equals 1, and then x equals 6. Okay, so it looks like it's vertically simple. In particular, y equals x looks like this. Y equals 6x. Instead of, this would be up 1 over 1. So 1, 2, 3, 4, 5, 6. Up 6 over 1 is this curve then. And then I'm going from 1 to 6, 2, 3, 4, 5, 6. And of course, I haven't given myself enough room to draw that. Somewhere up there. and then I have this vertical line at x equals 6 and a vertical line at x equals 1. So it's this region here that I'm super worried about. Unfortunately, to do that in the non-standard orientation, running up the flagpole, whoops, the dude has got a weird arm there. In order to do that, I got to split it into two regions, right? So it's going to, I don't even know if we can get a nice way out of it. Hopefully I've not drawn it all that greatly and we can actually split it once. Otherwise it looks like we're going to have to split it three pieces. Okay. But I hope I can just split it there, assuming that this point is directly to the right, horizontally to the right. Right. Okay, so I need to kind of hopefully figure out this region with an integral, and then figure out this region with another integral to make the software happy. So first off, I kind of need to figure out the intersections, right? So for y equals x, this point here is 1, 1. And then this point right here, when x is 6, y will be 6. So this will be the point 6, 6. I need to then figure out these point as well, these 2 points. Right? So those points are from the y equals 6x. And the first point is when x is 1, so that's going to be at the point 1 comma 6. So yeah, this is going to chop it into two regions perfectly. Okay, good. So then the top point there is when x is equal to 6. So this point will be 6 comma 36. Okay. Okay. Right. So I need to set up those crazy integrals in the weird orientation. So for the first region, I'm going the curve x equals something to x equals something, right? So x equals 1 to x equals whatever this curve is, right? So it's going from this curve to this curve. So it's x equals 1 to x equals x, or y, x equals y, sorry. So that's for the, and what is the function that we're integrating here? Let me find it. Y over x squared plus y squared. Let me put it in black. So the first one is dx because it's going from x equals 1 to x equals y. And then dy, I need to go from y equals 1 to y equals 6. And you could just literally look at the y coordinates of those points. Okay. So that's the first integral. And the second integral, again, y all over x squared plus y squared dx dy. So in the second integral, kind of maybe put it in yellow, I'm going from this curve to this curve. The first curve is the 6x, or rather 6y, I guess. I guess we're going to need to rewrite it, right? So taking, it's that curve, but I need to rewrite it so it's x equals. So y equals 6x, x equals y over 6. So x equals y over 6 to x equals 6. And then on the y-axis, I'm going from 6 to 36. Okay, and that is not an integral I wish to do, but I think the question asks for that answer, so I need to. Okay, can you give me the little bar thing so I can move that over and see it? Thank you. And right, so this one, going from 1 to 6. 1 to y, 6 to 36, and then y over 6 to 6, and then we want to rewrite it in the other orientation, right? So in the other orientation, hopefully it'll be just one integral. Yeah. So this time the running man is going in this direction. pretending he's twisting his arms all over the place, just going nuts. So that the curve to curve x equals this bottom curve now. So let me put it maybe in blue, I guess. This curve to y equals to y equals, right? So it's y equals, in this case, x. Okay. So the inner integral now is in terms of x. It's y equals to y equals. So dy dx. So y equals x to y equals 6x. And then point to point, looks like I'm going from 1 to 6. You just kind of look at the x coordinates of the points. So 1 to 6. And then we could, type that in. So 1 to 6. And then x to 6x. And then we want to evaluate that curve. So with respect to y, you could do a u sub. So u is x squared plus y squared. Du with respect to y is going to be 2y dy. And that will give you dy equals du over 2y. So my integral becomes y all over u times dy, which is du, all over 2y times dx. So that will become the integral. The y's cancel, 1/2 pops out, and you get du over u, so that's just a natural log. So this will be the integral 1/2 of the ln of the absolute value of, in this case, x squared plus y squared. And dx. Ooh, really? This integral isn't any easier. All right, so let's put in the limits and see if we can go from there. You could factor the 1/2 completely out of the integral. Anyways, this will be ln of x squared plus 36x squared. So it's going to end up being 37x squared. And then minus ln of x squared plus x squared is 2x squared. You could use properties of logarithms probably to simplify that. I don't know if it's worth it. I don't know if it'll even work. So what are our limits? 1 to 6. I mean, if you use the properties and limits, what do you end up getting? Let's just see if it works, right? So it's the ln of 37 halves, right? And then we could just evaluate that with respect to x. So that would be 1/2 ln of 37 halves x from 1 to 6. I hope that works. And it's putting in a 6, that would be 3 halves ln 37 halves minus just plain old 1/2 ln 37 halves. Is that right? 6 over 2. So 6 halves, sorry. Subtracting those, you get 5 halves ln of 37 halves. And I hope that's the answer. 5 halves ln of 5 halves ln of 37 halves. Of course, they give me the extra parentheses that I don't want. Oh, it worked. Sweet. All right. Well, there's that. So those can be quite challenging. Anyways, at the end, what they're going to do is start giving you all kinds of pictures, and you kind of have to figure out the integrals for these. Fortunately, most of them seem fairly simple. I don't know about these later ones. And then there's some of those. Okay. So let's look at one of these surface ones. Use a double integral to find the volume. All right, and basically it's just, find an integral that will kind of represent the region that you're integrating over, and then on the inside the integrand you're putting the z function. Okay, so for example number 12, what are we dealing with here? We have the region marked off, and I'm going to put it in the xy plane just to make life a little easier on me. looks like y equals x, and then y equals 7. 6, 7. Okay, so it just comes about right there, and it's this region. So I need a double integral to deal with this. I'm going to go the standard orientation, curve the curve. So y equals x to y equals 7. Sorry. And on the outer part, point the point. So that's going to go from 0. And this point, of course, if the if the y coordinate is 7, the x coordinate is also 7 because the curve is y equals x. Okay. And so the point is going to go from 0 to 7, and then you just put the surface inside the integral, so 49 minus xy dy equals, and then dx. Okay, so let's see if that works. So we have the integral of, with respect to y, 49y minus xy squared over 2 from x to 7 dx. So we have integral 49 cubed. It's like 243 maybe. That's going to be my guess. 343, yeah, something like that. 343 minus 49x all over 2 minus 49x minus x cubed all over 2 dx. I think 49 minus put in x squared times x is x. Okay, that looks okay. Integral 343, I can combine these two guys, right, into negative 49x over 2. Or actually, it's going to be bigger. I subtracted them. It's minus minus. So 49 times 2 is 98. So you get 49 halves plus 49 halves is 98 halves x, and then plus x cubed all over 2, and then I integrate that with respect to x. That's 343x minus 49x squared all over 2 plus x to the 4th over 8, and we're integrating from something to something, 0 to 7. And then I'm just going to go to Wolframize it. 343 times 7 minus 49 times 7 squared divided by 2 plus 7 to the 4th divided by 8. Wolfram doesn't even like that, so I'm not going to figure that out. Oops, I put a equal sign in there, no wonder. I like that better. 3, 1, 2, 1, 3 all over 8, which seems crazy to me. But you know how it is. 3, 1, 2, 1, 3 all over 8. We'll roll the dice. And it's wrong. Okay, so I got to find my mistake. Hold on. Oh, I see. It's right here. This would be 2. This would be 98. So it's actually 98 plus 49. 17. 107. Really? So I need to replace this with a 107. Which totally doesn't seem right either. 49. It's basically okay. So sure, whatever. Let's put a 107 in there and see if it's happier. The number don't look any prettier. I'll tell you that much. 4, 2, 5, 8, 1 all over 8. Well, first off, if I did do, there's going to be a 4 down here, right? So let's put that all over 4. Still don't look any prettier. 32095 all over 8. Let's try that. 1/5 all over 8. Still wrong. Pause. Now I can see I made an addition error. So 17, carry the 1, it's 147. Okay, so let's try this again. It's 147. This will be 147. This will be 147. This is like my 4th try. It's just getting ridiculous. So this is 147. 36015 over 8. I think that's my 4th, yeah. 36015 over 8. Let's see if it's happy about that. Still not right. At points like this, you start getting like, did I just do something? One way to get around it is to kind of just do the integral. So 49 minus x y with respect to x equals x to 7. So that part right there is the inner integral. And of course it didn't help very much. With respect to y, sorry, y equals x to 7. That doesn't have really much in either. So it'd be 49, yeah, there it is. So 49y minus xy squared over 2. 49y minus xy squared over 2. And then integrate that thing with respect to y. And see if it'll give you an indefinite so you can check. Whoops, it didn't like that. X with respect to x. Okay. Still doesn't like that. X equals 0 to 7. 7203. So it's somewhere on. It's on my part. Whatever I did something wrong in the evaluation. So at least I know it's not just, you know, I'm doing it right. I just set it up wrong. So let me take another look. It's almost like I got to redo the integral. So I know this part's right. 49y minus x squared, xy squared all over 2 from x to 7 dx. So that's going to be the integral 49 times 7. 343 minus y squared 49x all over 2 minus, now you plug in x, so you get 49x minus x cubed all over 2 dx. So this would be 343 minus, you need a common denominator there. It's like I'm not even going to trust my addition at this point. So 49 times 2 is 98, and then 98 plus 49 is 147. So 147x all over 2, and then no, that's not it, plus x cubed all over 2 dx. Reintegrate. So this will be 343x minus 147x squared all over 4 plus x to the 4th all over 8, which is kind of exactly what I had last time, right? I'm putting in 0 to 7. So this will equal, I mean literally that's what I kind of do, and then I just used Wolfram to figure it out. So 343 times 7 minus 147 times 49 all over 4 plus 7 to the 4th all over 8. Yeah, I got it now. I don't know what the heck I was doing wrong. 7203 all over 8 let's see if that works now. I apologize. I mean, I don't know what's wrong with me today, but probably it's the weather. It's raining out. I have a huge headache. I'm going to blame the weather. Alright, so there's that. So hopefully you kind of get the idea. Number 14 is an infinite integral. So you see this kind is kind of like something you would see on a probability exam. You're integrating underneath a probability function. Anyways, yeah, the region x plus y all over 2, and then let's do the regular order dy dx. So 0 to infinity and 0 to infinity. So the way you handle these is basically two improper integrals. So we have a limit as b goes to infinity of the integral from 0 to b of e to the negative x plus y all over 2 dy dx. Okay, so you need to kind of figure out that inner integral if it can be figured out. So I have the integral of, you could do a u sub, but you're going to get a negative 1/2 and then negative 2 popping out. So limit as b goes to infinity. And I know I shouldn't be doing stuff in my head anymore. I think I lost my credentials on that last problem, but there it is. Negative 2, basically it would be e to the u, back subbing e to the negative x plus y all over 2 from 0 to b, and then dx. So this would be the integral of the limit as b goes to infinity of negative 2e to the negative, what is this going to be, b plus some y, some constant, all over 2, minus negative 2e to the y all over 2 dx. I'm plugging in for y, not x. Oh, sorry. So it's actually plugging in for y. You get x plus b all over 2, and the other guy would be just x over 2. And you could tell because I'm going to be integrating with respect to x, and if I had an expression in terms of y, I wouldn't be able to. I mean, you could do it, but it wouldn't give you an answer, right? So anyways, the limit of this first part, as b goes to infinity, you just assume x is some constant, right? So like 5. You have b plus 5 over 2. As b goes to infinity, b plus 5 over 2 will go to infinity. So you'll have like e to the negative infinity. E to some negative like 1 billion is really, really close to 0. So this whole first part is going to zip off to 0. The second part isn't dependent on b, right? So you just get what you get. It's just 2e to the x over 2 dx from 0 to infinity. And then you do this integral. So again, if you did a u sub, you get a 1/2, and then divide by 1/2, it give you a 2, so another factor of 2. So before e to the u instead of u, x over 2. And we want to take the limit as b goes to infinity, so replacing that upper limit with a b and a 0 on the bottom. What would you get in that case? Right, so this should have a negative in there. I lost my negative. Okay, so that's going to be the limit as b goes to infinity of 4e to the negative b over 2, which that thing will go to 0, and then minus 4e to the 0. E to the 0 is just 1, so minus 4. So, whoops, I lost a negative. If you did a u sub, it'd be negative 1/2, because I did the u sub before I remembered to put the negative in there. So there's a negative floating in there. So that'd be negative. This is positive, and you'd end up with a 4. Because again, this thing would just go to 0. Okay, so 4 is the answer, I hope. Yay. All right. So bounded, so there's two functions that are bounded. I'll look at this number 18. Basically what you want to do is first figure out the region you're integrating over, and the region you're integrating over will just be the projection of this circular region onto the xy plane. Okay, so in number 18, we're trying to find the region between these two surfaces, right? So if you have this thing, kind of this looks like an oval type cross section. Okay. You want to find the volume of this kind of like contact lens region. What you want to first do is project that intersection into the xy plane. So so let's see what the curves are, right? So z equals 36 minus 6x, and z equals 36 minus x squared minus y squared. So you could literally just, I think you just set these two equal to each other, and you'll get that projection in the xy plane. So 36 minus 6x equals 36 minus x squared minus y squared. So you get x squared plus y squared minus 6x equals 0. Yeah, and so the projection of that thing is, and I think that the way I've drawn it is not completely accurate. It's kind of like it's like this, more like that. So your y-axis is right there, and the projection is going to be in the xy plane. It's just going to be a circle, right, like that. If you projected that thing down, it's a terrible picture, but hopefully you see what I mean. So in the xy plane, let's complete the square. I have x squared minus 6x plus negative 6 over 2 is 3 squared is 9 minus 9 plus y squared equals 0. So I get x minus 3 squared plus y squared is equal to 9. And so I have an ellipse, no, actually a circle just shifted. Plus y squared over 9 is 1. So 1, 2, 3 is the center. The radius is 3, so 1, 2, 3. And so the projection of that thing into the xy plane is actually this. 2, 3, 1, 2, 3. And then to get the volume in this little contact lens kind of region here, what I need to do is basically just integrate from the plane to the bubble region that's given by the other function. Okay, so it's basically like you're going surface to surface, curve to curve, point to point, ultimately. So what? The bottom surface is the plane. So the bottom surface would be 36 minus 6x. Whoops. And the top guy is going to be the paraboloid type deal. So the 36 minus x squared minus y squared. If you found the double integral of that, that would find the volume underneath the paraboloid over top of the circular region. Okay. If you then kind of subtract away the volume underneath the plane, then you would get the volume between the paraboloid and the plane, right? So you subtract away this 36 minus 6x, but you could just combine that into one integral. Let's do the standard orientation, dy dx. Okay. So your double integral is going to be the 36 minus x squared minus y squared minus the 36 minus 6x. Like that. Okay. And then you got your dy dx, and then our region that we're integrating over, dy first. So the bottom curve blue to the top curve I'll put in red, or try to put in red. Here's my running guy going in this direction. So point to point is going to be 0 to 6. Okay. So the outer part of the integral is 0 to 6. The inner portion then, solving this equation for y, I get y is plus or minus the square root of 9 minus x minus 3 squared. So the bottom branch is the negative square root, the top branch is the positive square root. So I got negative square root of, what did I say? 9 minus x minus 3 squared to the positive square root. And this is going from 0 to 6. The top one is 9 minus x minus 3 squared. Okay. Right. So in the integral, you see they cut it in half. So what they're saying is there's some symmetry involved. So basically, you can integrate. You're going to have to be careful about it because it's not quite, symmetric. Seems like you can have the running man go from here to here, but then you would still need those other bounds. So that's kind of crazy how they do it that way. So it seems like just from symmetry, I'm going to be able to kind of cut it in half and just integrate from 0 to the top curve. But if you do cut it in half like that, then you have to multiply the outside by 2. Okay. So if you do cut it like this and go that, you have to tack on a 2 on the outside, and then we should be good to go, I think. So this will be 2 double integral 0 to the square root 9 minus x minus 3 squared, and then 0 to 6. Simplifying a bit, 36's are gone. So you get 6x minus x squared minus y squared dy dx. Okay, so let's toss that into the formula and see if it's happy about it. Submit answer, see what's up. Yeah, I liked it. Okay, great. Another sketch region. Average value, again, it's just like a probability thing. For average value, the formula is going to be 1 all over the area times the double integral of the function over whatever region you're dealing with. Dy dx or just dA. Okay, so in this case, the region we're integrating over 0 0 4 0 0 3, and then so it's a rectangle, no big deal. The area of that rectangle then is just going to be 12, so it's going to be 1/12 times the double integral. The function is x. Let's go dy dx. On the x-axis, y equals to y equals, right? So curve the curve, y equals, it's almost easier to put it in the xy plane, right? 4, 3. So y equals 0 to y equals 3, and then x equals 0 to x equals 4. Okay, so this would be 1/12 integral x y from 0 to 3 dx. That would be 1/12 integral still of plugging in 3 for y, so 3x dx, and then integrate that from 0 to 4. So get 1/12 3x squared over 2 from 0 to 4. So that'd be 1/12 times 16 times 3, 48 over 2 is 24. So I'm thinking it's 2. I'm just going to shoot from the hip there. Plug that in, see if it works. Yeah, Okay, so there's that. So for these ones where you're having solid regions bounded by surfaces, you want to find the volume of the solid bounded by the graphs of the equation. Yeah, surface to surface. I don't think that's one of them though. That's just over the XY plane, I believe. This video is long enough. Let's just leave it there, and I'll leave the rest for your homework. Thank you for watching, and I'll see you next time.